Congratulations. You've made it all the way up to number 25. The hard part about this problem is that there are so many nines, and it really gets confusing if you're not careful. You have a design on the floor, on a bathroom floor, and it has 9 circles, and the innermost circle has 9 tiles, and each one has 9 more tiles than the one before it. And knowing that, you need to keep in mind that this is going to be a sequence. This is going to be a list of numbers. So this is going to be like circle 1, and then we're going to have circle 2, and then circle 3. And, you know, we could just call it what it really is. This is A sub 1. We used to call it A sub 0, A sub 2, A sub 3, A sub 4, A5, A6. Whoa, where do we stop? How many? 9, because everything in this problem is a 9. A7, A8, A9. Okay, so in the first circle, which is A sub 1, you have 9 tiles. There's some funny design on your bathroom floor. Now, honestly, when I first read this problem, I had a hard time visualizing what it was really getting at. I didn't know what it was really saying. Because you have these tiles, and it makes a circle, and there's another circle, and there's more tiles, and like, you know, like when you see the design on the bathroom floor, that would be a hideous bathroom floor. But nevertheless, somebody has it, and it starts with 9 tiles. And then the next one has 9 more tiles, so 9 plus 9 is 18. And then we have 27, and then 36. You can see where this is going, and you can probably tell where it's going to end, and you're probably already there if you're ahead of me. So yeah, 45, 54, why did I hesitate? I'm embarrassed now. 72 and 81. Okay, and we're going to keep that in mind. Now, we can add them all together, but I want to take this opportunity, I want to use this opportunity to use a different formula. We're going to be finding the sum of a, wait a minute, what kind of sequence is this? Is it arithmetic or geometric? Are we adding the same thing every time, or are we multiplying by the same thing every time? So this is going to be the sum of an arithmetic sequence. Arithmetic, actually series, if we're adding it we call it a series. And knowing that, we're going to write the formula. So the sum of the first 9 terms is going to be n over 2 times a. Now in our formula originally it was a, yeah, it was a 1. No, it was a 0. Nevertheless. First term plus last term. Sorry, I'm complicating things a little bit, and I don't mean to. But in our formula, that was a 0, and that was an n minus 1, but we've kind of reset things a little bit. Basically, first term and last term. And I'm going to write that down, just so we can remember. Number of items, that's first, and that's last. Okay, so here we go. We have 9 things in our list, 9 divided by 2, and the first one is a 9, the last one is an 81. This goes back to Gauss's thing. I want you to make that connection. Remember when he was a kid and his teacher made him add the first 100 numbers to keep him busy, and he was done in like no time at all? Remind me to tell you something cool about Gauss in a minute. If I don't tell you at the end of this video, then just come up to my desk and ask me, and I'll tell you something cool. And what he would do is he would pair the first and the last one, and then you'd pair those, and he'd pair those, and this is what that formula is based on. There are 9 things, and when we pair them up, we have 4 and a half. 9 divided by 2 is 4 and a half. We have 4 and a half pairs if we were to pair them up, and pairing them up is going to give us the same sum every time. So 4 and a half times 90, 4 and a half times 90, let's see, 4 times 90 is 300. I'm doing math sort of in my head, on the board too. So 90 times 4, and then half of that is 45. So the answer is 405. 405. There we go. Oh, Gauss. Thanks for reminding me. Gauss was such a genius. He was an amazing genius. He was a prodigy, and it was obvious when he was in elementary school. But back in Greek times, by the way, Gauss lived in the late 1700s, early 1800s. So he, was born in like 1777 and died in 18-something. I don't remember exactly. But he was a total genius. But back in Greek times, like during the Greek Empire, there was a man by the name of Euclid, and he wrote a book, very long-lasting book. I have a copy of it, actually, and not an original Greek scroll, but it's a very widely circulated book, and it's been around for, obviously, for centuries. And within it he talks about the different things you can do, the different constructions you can make using just a straight edge and a compass. And it's an unmarked straight edge, so it's not a ruler. And he's talking about, like, you can make hexagons and you can make squares and you can make triangles and you can construct these things. And it was the foundation of a lot of geometry. And people thought that you could only make certain figures. And actually, I'm going to take this opportunity here to go a little bit further into sequences and series. So here we go. Back in the day, now that I brought it up, here we go. Back in the day, people knew that using just a straight edge and a compass, you could construct a triangle. And also, if you were to chop the sides in half and put a circle around it and do some craziness, you could also construct a hexagon. And if you were to chop those in half, you could construct a dodecagon, and you could construct that, and you could construct that. And you could construct this shape, and you could construct this shape, and I'm not even going to try to draw anything beyond that. 3 sides, 6 sides, 12 sides, 24, and they were all regular shapes. They also knew you could do a square, 4 sides obviously, and by putting a circle around it and chopping the sides in half, you could do this, and you could do this, and you could do this. Are you noticing a pattern here? These are all geometric sequences. Geometric sequences. And also, you can make a pentagon. It was possible to make a pentagon, and with that you could have a 10-sided figure, and you can make a 20-sided figure, and you can make a 40-sided figure, and an 80-sided figure, and it got kind of cumbersome, but it was possible. And so you could keep doubling them, and in case you care, and you should. In this case, r is equal to 2, because you're doubling every time, and in this case, r is equal to 2, and in this case, r is equal to 2. Well, where does Gauss come in? People thought that these were the only types of shapes, the only regular polygons like triangles, squares, octagons, 16gons that you could construct using a straight edge and a compass. Nowhere on here do you see some ridiculously odd numbers. Actually, the only odd numbers on here at all that you see are 3 and 5. Gauss, as a teenager, showed how to construct a 17-sided regular polygon. He was brilliant. He was an absolute genius.